The universe is far stranger than we ever imagined. For centuries, humanity believed that our solar system represented a kind of universal blueprint, a standard model of how planets should form and behave. Small rocky worlds near a star, massive gas giants farther away, and stable, predictable orbits governed by simple physical laws. It was a comforting idea that what we see in our cosmic backyard is what we should expect everywhere else. But that idea did not survive contact with reality. As our technology improved, as our telescopes became more sensitive, and as we learned how to detect planets around other stars, exoplanets, the universe began to reveal itself as something far more chaotic, diverse, and extreme than anyone had predicted. What we discovered was not a collection of solar system copies, but a gallery of alien worlds so strange they seem almost fictional. Today, thousands of exoplanets have been confirmed, and each new discovery expands the boundaries of what we thought was possible. Some of these worlds orbit so close to their stars that their surfaces are essentially oceans of molten rock. Others are so cold they are locked in eternal darkness. Some are so large and hot that metals vaporize into clouds. And some are so light and diffuse that they barely seem like planets at all. The universe is not just different from our expectations. In many ways, it actively defies them. One of the most well-known extreme worlds is HD 189733b, a gas giant located about 64 light-years away. From a distance, it appears almost Earth-like, a deep, striking blue sphere floating peacefully in space. But that beauty is an illusion. In reality, this planet is one of the most violent environments ever observed. Winds roar through its atmosphere at speeds exceeding 8,000 kilometers per hour, fast enough to circle the entire planet in a matter of hours. The atmosphere itself is filled with particles of silicate, meaning that instead of water rain, there are sideways storms of molten glass driven by supersonic winds. It is a world where the concept of weather becomes something hostile, destructive, and almost unimaginable. Then there is 55 Cancri, a planet that pushes the limits of both imagination and physics. Often described as a diamond planet, it is a super-Earth roughly twice the size of our own world. Its density and carbon-rich composition suggest that under extreme pressure, much of its interior could crystallize into diamond structures. But any romantic vision of a glittering gemstone world collapses under reality. Surface temperatures exceed 2,000 degrees Celsius. Vast regions are likely covered in oceans of lava, constantly shifting and reshaping under intense heat. This is not a jewel in space, it is a furnace wrapped in stone. Even more dramatic is WASP 76b, a planet where iron itself becomes part of the weather cycle. Tidally locked to its star, one hemisphere permanently faces intense stellar radiation while the other remains in eternal night. On the day side, temperatures are so extreme that iron vaporizes into the atmosphere. Strong winds carry this iron vapor across the planet to the cooler night side, where it condenses and falls as metallic rain. Imagine a sky filled not with water droplets, but with molten metal falling from clouds shaped by fire and darkness. Some worlds challenge not just our sense of environment, but our sense of time itself. PSR B1257+12, often called the Methuselah planet, is one of the oldest known planets in the universe, formed nearly 13 billion years ago. It orbits a binary system containing a pulsar and a white dwarf, stellar remnants that emit intense radiation and represent the final stages of stellar evolution. And yet, this ancient planet has survived through nearly the entire history of the universe, silently orbiting while galaxies formed, collided, and evolved around it. It is a relic from a time when the universe was still young. Other planets feel like science fiction made real. Kepler 16b is one of the most famous examples. It orbits two stars, meaning that from its surface, the sky would contain two suns. These suns would rise and set in complex patterns, casting shifting shadows and creating a world where day and night are never truly stable concepts. For decades, such systems were imagined in fiction. Now, we know they are real and surprisingly common. In contrast to these massive gas giants and extreme super-Earths, some planets are so light and delicate they seem almost impossible. Kepler 51d is a super-puff planet, roughly the size of Jupiter but with a fraction of its mass. Its density is so low that it has been compared to cotton candy. The atmosphere is extremely extended and fragile, raising a fundamental question. How does such a planet even maintain itself without being stripped away by stellar radiation? Its existence challenges our understanding of planetary formation and atmospheric stability. At the opposite extreme lies Trace 2b, one of the darkest worlds ever discovered. This planet reflects less than 1% of the light that hits it, making it darker than coal or even fresh asphalt. Despite orbiting very close to its star and experiencing extreme heat, it absorbs nearly all incoming radiation. In a universe filled with bright stars and glowing nebulae, this world is a shadow, a nearly invisible sphere drifting through darkness. Then there is K2141b, a planet caught in a cycle of destruction and renewal on a planetary scale. One side of this world permanently faces its star, reaching temperatures high enough to vaporize rock. This creates an atmosphere made of evaporated minerals, which are then transported by winds to the cooler side of the planet. There, the rock condenses and falls back to the surface as literal stone rain. Over time, this cycle reshapes the entire planet, constantly eroding and rebuilding its surface in a violent geological loop. But the strange diversity of exoplanets does not end there. Some of the most intriguing worlds are not the most extreme in temperature or composition, but in structure and environment. Proxima Centauri b, the closest known exoplanet to Earth, orbits the red dwarf star Proxima Centauri just over 4 light-years away. It lies in the so-called habitable zone, where liquid water could potentially exist. Yet its star is highly active, producing powerful solar flares that could strip away any atmosphere. If the planet has a magnetic field strong enough, or a thick enough atmosphere, life might still find a way. But it remains a world suspended between possibility and hostility. Kepler 22b was one of the first confirmed planets found in the habitable zone of a Sun-like star. It is significantly larger than Earth, possibly a water world, with global oceans covering its surface. If such oceans exist, they could be hundreds of kilometers deep, with no land in sight, an endless planetary sea under a foreign sky. Gliese 581 grams, though still debated in its confirmation, became famous as one of the early candidates for a potentially habitable exoplanet. It sparked imagination worldwide, representing the idea that Earth-like worlds might not be rare, but common across the galaxy. Even if its exact status remains uncertain, its impact on exoplanet science is undeniable. Beyond individual planets, entire categories of worlds have reshaped our understanding of planetary systems. Hot Jupiters are gas giants that orbit extremely close to their stars, far closer than Mercury orbits the Sun. Their temperatures are so high that their atmospheres expand and sometimes evaporate into space, forming comet-like tails. These planets likely did not form in place but migrated inward, disrupting any smaller planets that might have once existed. There are also rogue planets, worlds that do not orbit any star at all. Instead, they drift through interstellar space in complete darkness, warmed only by internal heat left over from their formation. These planets are essentially cosmic nomads, traveling through the galaxy unseen and unbound, their origins often unknown. The method by which we discover these worlds is itself a testament to human ingenuity. Most exoplanets are found using the transit method, where a planet passes in front of its star and causes a tiny dip in brightness. Others are detected through the radial velocity method, where a star wobbles due to the gravitational pull of an orbiting planet. Each detection is a careful measurement of tiny signals buried in vast cosmic noise. In recent years, advanced instruments like the James Webb Space Telescope have begun to analyze exoplanet atmospheres in unprecedented detail. By studying the light that passes through or is emitted by these distant worlds, scientists can begin to identify chemical signatures, water vapor, carbon dioxide, methane, and more. For the first time in history, we are not only discovering planets, but beginning to understand what they are made of. And with each discovery, a deeper truth becomes clear. The universe is not built around simplicity. Planets can be molten or frozen, dense or airy, stable or chaotic, familiar or utterly alien. They can orbit one star, two stars, or none at all. It can rain glass, iron, or stone. It can be older than most stars in the galaxy or so young they're still forming. They can reflect light like mirrors or absorb it until they vanish into darkness. And somewhere, hidden in this vast diversity, there may even be worlds that resemble our own, not as copies, but as rare outcomes of the same physical laws. The more we explore, the more we realize that Earth is not the template. It is just one expression among countless possibilities. The universe is not just large. It is endlessly creative in ways we are only beginning to understand. And every new planet we discover is another reminder that reality is far stranger than imagination has ever been able to predict.